My name is Joseph Turian. The title of my talk is New Developments in Large Data That Have Immediate Applications in Industry. So I was talking with Pete Skomrock of LinkedIn earlier, and he was like, Joseph, I'm very excited for your talk, but I'm also really worried. Because in my talk, Joseph, I only had 2 equations. I said, Pete, you're a great speaker and all, but that's 2 equations too much. This is supposed to be a fun talk. I hope it's very accessible. There are no equations. It's not aimed at technical people, it's aimed at big picture thinkers. On the other hand, I am going to move very fast. If you want to catch it all, my recommendation is to close your laptops. If you want to leave them open, it's fine. Just follow me on Twitter. Turian is my Twitter username. So, what are we talking about today? Well, the talk is about how do you get a competitive advantage with data. One approach, just use more data than everyone else. But if you look to the people to your left and the people to your right, they're already probably using a bunch of data. They already know about this trick. It's becoming more widespread. It's harder to eke out a competitive advantage by using more data. Another approach to getting competitive advantage is to use better algorithms. So I'm going to argue when big data gives you diminishing returns, that's when you need to turn to better algorithms. And you can tweet me on that. In fact, if you go to my Twitter account, you can retweet me on that. So when should you use better algorithms? Well, I'm a big proponent that if you have a really cool algorithm, then you should use it. Okay, not really. So when should you use better algorithms? If you have a lot of time on your hands, you should use better algorithms. No, that's not right either. In fact, you should only use better algorithms if they will qualitatively improve your product. I'm going to talk about some interesting new algorithms that will qualitatively improve a lot of tasks in big data. I'm not saying that you should always use the most sophisticated algorithm. In fact, I'm a big proponent of simple is better. But if you want to know what's on the horizon, this is what this talk is about. So, who am I? Just by way of introduction. If you don't know me, my name is Joseph Turian. I've been a hacker or a coder for about 20 years. I used to program competitively at a world-class level. In addition, I have a PhD that I got from NYU. I've been spending the last 10 years working on large-scale machine learning and natural language processing problems. What is MetaOptimize? I feel like MetaOptimize was this. So MetaOptimize, it means to optimize the process of optimizing the process of optimizing yada, 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 yada. But more seriously, what MetaOptimize is my consultancy. Our sweet spot is large-scale machine learning and natural language processing with well-engineered solutions. Other people that have actually been working on machine learning and natural language processing might know MetaOptimize because it has a very well-known Q&A forum where machine learning and natural language practitioners, as well as big data guys in general, can come together, ask each other questions, and share knowledge. It's actually a very popular site. I think it's the most popular site, hands down, for machine learning and natural language processing on the web. It has about 1,500 unique visitors a day, and is just a tremendous resource. So anyway, here's what I'm going to talk about. There are 4 different algorithms that I'm going to put forward that you should know about. The first one is deep learning. So deep learning, here's the opportunity. If you want to do machine learning that's large scale, that can use all sorts of different data, heterogeneous information, combine it all together, as well as being general purpose and highly accurate, that's what deep learning is going towards. And deep learning is something that came out of the literature on artificial intelligence. So artificial intelligence, right? 50 years ago, what was artificial intelligence? It was something that was going to happen in 10 or 20 years, 1960, 1970. We'll have it all solved. The original artificial intelligence scientists overpromised and underdelivered, and it really put a bad taste in everybody's mouth. And for a while, artificial intelligence really was out of fashion. It was like a dirty word. But now it's back. There are a group of researchers who believe ambitiously in artificial intelligence, but they're not overclaiming. They're using methodological science to make progress, but always with the goal not to work with toy models, not to work on toy problems, to work with models that have a plausible shot at solving artificial intelligence. And this is why they developed deep learning. So let's talk about artificial intelligence for a moment. Well, natural intelligence, as we know, works. But on the other hand, artificial intelligence, as I said before, has not really lived up to its goal. And the question is why? Well, to get at this, let's start with what is intelligence? Where do we get intelligence? So I would argue that we get intelligence from knowledge. And so the question is, how can a machine acquire knowledge? Okay? I think we all know that the right answer is get a bunch of people to sit around in a room with terminals and start encoding knowledge into a computer, right? Now, in fact, intelligence comes from knowledge, and knowledge in the human space, and as far as we know in the artificial space, should come from learning. And you can tweet me on that. So, to wit, a new field has arisen called statistical learning. It has numerous applications, including finance, speech, robotics, medicine, music, etc. It's also known as machine learning, but if it uses statistics, it's specifically statistical learning. And statistical learning really is trying to get the problem of generalization, not memorization, which would be the human encoding everything that we already know model, but how do we actually generalize to new circumstances so that we can adapt, compete, and cooperate? So how do we build a learning machine? I'm going to talk about the deep learning approach for now. So if you see on the bottom of the screen, let's talk about a vision system, a vision model. Well, at the bottom, it receives its input raw pixels looking from an image, right? Then it takes these pixels, passes them to a feature extractor, and that feature extractor will pull out edges, okay? Then that feature extractor will pass the edges as output to a higher level feature abstractor, which will now pull out shapes. That higher level feature abstractor will take those shapes, pass them to a higher feature extractor in the pipeline, and then get faces. And then we can really start doing reasoning, because once we recognize faces, we can be like, is this Bob, is this John, is it Joseph, etc. So what you're seeing here is a pipeline in which some very primitive, low-level retinal input becomes progressively more and more abstract and high-level as we pass it through this feature extraction pipeline. And this is the idea behind deep learning. Okay? By comparison, a shallow learning architecture is one in which there aren't many stages of feature extraction. You go almost directly from the input to the output. Most of the machine learning algorithms you might be familiar with: naive Bayes, logistic regression, decision trees, support vector machines. Basically everything that's in common practice right now is a shallow learning architecture. And I'm going to show you why this might be problematic. So why do we want deep architectures? Well, let's talk about a computer program, right? In a computer program, we have the main routine calls subroutines, the subroutine calls sub-subroutines, etc., etc. And there can be arbitrary levels of abstraction, right? Abstraction is a powerful tool in computer programming. Now let's say I were to say to you, okay, well, I want you to code something, but you can only use one level of abstraction. You only have subroutines, no sub-subroutines, right? You could still write every program that you wanted, but you'd have to do a lot of code copying. And in this way, you end up with a representation where your code is just much more redundant. You're not able to share information, and that's the power of abstraction, that's the power of depth. If you look at computer circuits or electronic circuits, they're also deep. From the input to the output, you pass the input through a variety of possible gates to transform it. Okay? Whereas a shallow circuit, mathematically, can actually express everything that a deep circuit can, but it requires that the circuit be really, really fast. Okay? So if we're talking about a very shallow architecture, we end up with something fat and wide, whereas we have something much more compact if we start using depth and abstraction. Okay, so what's wrong with a fat architecture? Well, so the problem is overfitting. That once you start introducing a lot of parameters, it becomes very difficult to generalize correctly. Your model just becomes overly complicated. And to go back to the principle of Occam's razor, we don't want something that's more complicated than is necessary. We don't want computer code that needlessly copies and pastes. That's just error-prone. So what are some other motivations for deep architectures? Well, let's look at the brain. More particularly, let's look at the visual cortex. The visual cortex, to the best of our knowledge according to current neuroscience, is a deep architecture. In fact, it's very similar to that deep architecture that I showed you earlier, where the retina passes pixels to the V1 area, that does edge detection, those edges go to V2, primitive shape detection, and as far as we know, V4 has higher level visual abstractions. So the visual cortex is also a deep architecture. So I've argued both from intuition and circuit theory and neuroscience that we want deep architectures, right? But what's the problem? What's the catch? Well, the catch is that they're hard to train. And in fact, up until 2006, we really just didn't know how to train them. Didn't know at all how to train them. So what happened in 2006, there was a breakthrough. And what it was, there were several different training techniques that were introduced for these deep architectures. Because everyone was like, deep makes sense, but we just can't use it. So in 2006, a handful of scientists came up with a few training techniques. One, you increase the signal-to-noise ratio in training. Two, you do unsupervised learning, which is the model essentially learns to model the input without any specific task in mind. It just learns about what's around it. And lastly, that you do this feature extraction one layer at a time. Okay? And this work was done in 2006, it was started at that time by three gentlemen, Yasha Benji in Montreal, Jeff Hinton in Toronto, Jan Kuhn in New York, where I actually got my PhD. As I said, in 2006, I submitted my thesis, and I wasn't sure what I wanted to keep working on. I knew I wanted to work on large-scale machine learning, and I just found this wacky tech report. It was not published yet, and it was on this deep learning stuff. And I was like, wow, this is not just very ambitious, but it's also very methodical and effective. And I think this is going to be important. I spoke to all three of these men, and it was very clear that I wanted to work with Joshua. And it turns out they were right. It turns out that deep learning is now becoming a big deal. It's broken records in many different machine learning tasks, especially considering that it hasn't used any very specific tuning. That's very impressive. Second of all, it's become very popular in the artificial intelligence and machine learning community, and it's even gotten the attention of government funding agencies like NSF and DARPA, who are now funding deep learning research specifically. So, as I said, the opportunity with deep learning is large-scale machine learning that's highly accurate and general purpose and not task specific. Okay, so that was deep learning. I'm going to talk about a specific application of deep learning called semantic hashing, which I think is pretty darn cool. So, what the opportunity here is fast semantic search. Okay? And the question is, okay, what do you mean semantic search? Why can't we just do keyword search? Well, let's just say that we are doing keyword search and searching Twitter for tweets on to do, right? Well, I think we all know what's going to happen is that we're going to miss a lot of relevant tweets. If it says HBase, not to do, you miss it. If you say Amazon Elastic MapReduce, you miss it. Okay? So keyword search misses a lot of relevant results, which is why we like to include semantics. And not just primitive semantics, not just synonyms, but real semantics. Okay? So as I said, keyword search misses relevant results. And here's the data structure we use. Now keyword search is actually really fast because it's this data structure called the inverted index. So if I were looking for articles on blog, they contain the word blog, then the inverted index contains pointers to all the documents that contain blog. And we can do this search in essentially constant time. Right? Now, hashing is also essentially a constant time technique. It's another technique for search that's also really fast. And how it works is we take the document, we hash it to a bitwise address space, and then we find the documents that are nearby in this address space. And these documents, if we have the hash document, should be similar to the input document. So it's also very compact. Without hashing, if we want to have billions of images, the features would take about 40 terabytes. Whereas with the 64-bit hash function, we can store billions of images on commodity hardware. In fact, a single PC. I think that's pretty cool. So hashing has actually been around for a while. There are a lot of hashing techniques that you may have heard of or may not have heard of. Locality-sensitive hashing, bloom filters, random projections. these have been around for a while, and they're effective, they're good. The reason I call them dumb is not because they're not good, but because they're ignorant to the data and ignorant to the task at hand. They don't do any learning, they're not data-driven. Now, smart hashing, on the other hand, is just as fast as dumb hashing. In fact, it can be faster, depending on the hash function. But it's data-driven, and it's become much more popular in the last few years. I'm going to talk specifically about semantic hashing. So what is semantic hashing? Okay. Semantic hashing is when you combine smart hashing with deep learning. Some of you in the audience are looking at me. Okay, so I apologize. I actually have one equation in my talk, and this is it. So here's what happens in semantic hashing. I take the input, it's all the way in the bottom, and then I keep compressing it and doing this feature extraction, but I learn the feature extraction so that I have this 32-bit code in the middle that's a highly compressed representation of the original document, and I train it so that these 32 bits can decompress the original 2,000 bits, okay? And that's the general idea. I'm going to use a deep architecture to compress each document, and that compression is its code, okay? And things that are nearby in code space are semantically similar. If you haven't heard about these techniques, don't worry, but if you want to compare them to sort of shallower techniques, TF-IDF would be no feature extraction of the initial document. Latent semantic analysis, latent semantic indexing, LDA, latent Dirichlet allocation, these are all shallow feature extraction techniques of the original document, as opposed to semantic hashing, which is deep. So just to sort of illustrate what could happen, if I were to try and compress using the semantic hashing and then visualize documents in 2D space, and then just color in the documents that have similar topics, the semantic hashing didn't know about these topics, but has nonetheless put like articles and like documents really nearby. And I think this just kind of visually illustrates what the semantic hashing is doing and how it's able to actually make things that are related be very close together in their code space. So the opportunity, as I said, is semantic search that is general purpose, fast, and compact. It's general purpose because you can stick anything to it, right? It's been done not just in text, it's also been done in images. There's no reason the principle can be used on videos, audio, time series, etc. It's fast. A small organization could just index 1 billion documents in a few weeks. I think that's pretty good. Besides that, retrieval is very fast. 3.6 milliseconds if you have 1 million documents. And it doesn't scale linearly, it scales up linearly. So don't quote me on this, but my guess is that for 1 billion documents, it might be 10 or 100 milliseconds, not 1,000 times as low. Lastly, these representations are compact. You can store the index for 1 billion documents, 1 billion images on commodity hardware. And here's my prediction. Smart hashing will revolutionize search. You can tweet me on that too. All right, graph parallelism, next step. So, if you've been following the non-relation database movement of Cassandra, Voldemort, Redis, Mongo, etc., you can see that there are more and more of these non-relational data stores. Now, with the rise of linked data, there's actually been, even more recently, the rise of non-relational graph stores, most famous of which is Neo4j, but there are a handful of others. So this points to increasing movement towards graph analysis. And here's the opportunity with graph-based parallelism. I don't think I need to sell you on like parallel training or parallelization of algorithms. What I do need to sell you on is that if we really want to do this on sophisticated machine learning algorithms so that we can scale them to many examples and get higher accuracy, that we're going to need a graph-based parallelism approach. So there's many useful machine learning algorithms that are commonplace: matrix factorization, expectation maximization, lasso, etc. These all have graph-based data dependencies. Okay? So let's take these sophisticated machine learning algorithms and try and put them in MapReduce, right? Do you know what's going to happen? So, Carlos Western actually calls this MapAbuse. Arguing is kind of like putting a square peg in a round hole. That MapReduce is not well suited when there are graph-like sparse dependencies in the data. And what will happen is if you try and map-reduce these algorithms, you're not going to get as good parallelism as you should. The parallelism will fall off. And as I said, the reason for this is that the MapReduce paradigm, parallelism abstraction, is slightly too high level for these graph-based data dependencies. What we need is something slightly lower level, where we don't need to worry about concurrency or locking or synchronization, but that nonetheless can work with graphs. And this is what's been happening recently. Google has Pradle. Their implementation is proprietary. In October, there's an Erlang-based implementation providing GitHub called Phoebus. GraphLab by Low et al. They actually released the source code. That's another graph-based parallelism technique that you can use for training these machine learning algorithms. So just to come back, this is my last plug for the talk. I went on the MetaOptimize Q&A talk when I saw the preprint of the GraphLab paper, and I was curious about it. I went on the site and I just asked. I was like, when is it preferable to MapReduce? When, and vice versa. And one of the authors for the paper that actually came onto the site and he responded. It was actually the first public discussion of GraphLab on the web. So I guess this is why I'm trying to stress that the Q&A forum is a valuable resource if you're interested in talking to very experienced people and picking their brains about natural language processing, machine learning, and the people in your office, in your group, don't know the answers. So the opportunity with this graph-based parallelism is that we'll be able to more effectively scale many commonplace machine learning algorithms. And my prediction, MapReduce will still be used for simple algorithms, but for more sophisticated machine learning algorithms, you're going to need graph-based parallelism. And you can tweet me on that. Last one, unsupervised semantic parsing. So what we really are getting at here is natural language understanding. That you take text, stick it in a machine without really telling it anything, that's just able to read the text and start learning. And we want something general and task and domain and specific, so that's not very brittle. Okay? And if we can do this, or if we can do it reasonably well, we don't have to solve it. If we can do it reasonably well, we can start doing much better on a variety of very useful applications, question answering, natural language search, et cetera, et cetera. So let's talk about question answering, right? Here's an example. If I were to say to you, let's just assume for the sake of argument, you don't know biomed, and you're as dumb as the computer. I don't know biomed. What does IL2 control, right? How would you solve that? Probably you'd have to go, and you have to read some articles on biomed. And if you were able to know that the word inhibited means control, then you'd be able to answer my question. And you'd be able to say, well, IL2 controls the DEX-mediated L-kappa B-alpha induction. But to do that, you'd have to know that inhibited means control. So the challenge here is that there are many different ways to say the same thing in language. So semantic parsing, how does semantic parsing attempt to attack this problem? Well, if we have the sentence, Microsoft buys power set, we can transform it into a formal knowledge representation where we say, okay, there's this thing, this meaning cluster called Microsoft, the meaning cluster called power set, and they are related by something called spies, right? So where does this intelligence come from? If you're paying attention, it comes from knowledge. The intelligence comes from knowledge. So what we're really interested in is knowledge extraction, knowledge acquisition, in a purely automatic way by reading text. More than that, we also want an ontology that understands the relationships between different meanings. We want the induce to know that induce is a kind of regulate, inhibit is a kind of regulate, activate is a kind of regulate. We also want to know that there are different forms that express the meaning regulate. We could say regulate, we could say control, we could say govern, we could say modulate. All of these things are word forms that are variations on the same meaning, which is regulate. So how do we extract this knowledge from the text? Okay. Well, there's really only, I think we all know that what we want to do is hire some linguists. They're going to sit down, write a grammar. It looks something like that. Oh, wait, no. We want an approach general purpose, abstract, automatic. And it might be possible, right? What's the problem with the manual approach? Well, it's costly, ineffective, and inflexible. For example, when we're talking about the different meaning variations, this is really hard to encode manually. Besides that, it's a very brittle approach. If you sit down and write a grammar for newspaper text, it's not going to apply to biomed articles, it's not going to apply to tweets, etc. We want to approach this general purpose and we can point to different domains without doing any sort of manual engineering. So what is it we want? Knowledge extraction that's large scale, open domain, automatic, and end-to-end. And we want to learn an ontology at the same time. If we have the ontology and we know that inhibit is a kind of regulate, then we're actually able to connect the meaning of the sentence with the question that's being asked. And then we begin to approach understanding. So we want ontology learning. Historically, this has been broken into 2 steps. We do induction, then population. Maybe we do it manually. Maybe we write some heuristics. But I've argued that there are a lot of problems with these approaches. So this work is really cool. When I read this work by Kuhn and Domingos, it was one of these things I was like, whoa. Like, in natural language processing, like a lot of the time, we're working on sub-problems, part-of-speech tagging, parsing, but that's not what we really care about. What we really care about is true natural language understanding. And a lot of the people in the field are daunted by that. A lot of people in our field are intimidated by that or lose sight of that. And Kuhn and Domingos just came out and said, we're going to really try and solve this in a completely automatic way. And it's like, whoa. And their approach, besides being completely ambitious, is also effective and elegant. I just think it's great. I'm going to tell you a little bit about it. So here's the intuition, right? We want to cluster different forms that encode the same meaning. So the meaning buys, we can express in different ways. We can say buys, acquires, as is purchase of. Microsoft, we can also say in a different way. The Redmond software giant, Microsoft Corp, etc. So how would we do this, okay? So you're given the text, we just take the text and we shove it into the machine. And then the first thing it knows is that Microsoft in blue always encodes the same meaning. Buys always encodes the same meaning in red. Power set always encodes the same meaning. And from there, we can start inducing knowledge. For example, if we know Microsoft buys PowerSet and also Microsoft something PowerSet, then that something probably means the same thing as buys. So we start just doing this clustering. We say, okay, well now we have clustered things into the meaning cluster buys. We have different words now in different forms that start meaning buys. Then we can keep going and say, okay, well now let's say, okay, semantic search engine PowerSet probably is the same thing as PowerSet. And we just keep doing this until we've tried to encode almost all the meaning, or until our explanations start being probabilistically implausible. Right? So we could say Microsoft Corporation, that's also the same thing as Microsoft. Okay? Then we end up with these clusters, and these clusters really start getting at the meaning, and then we can use them to actually do a variety of tasks. Like they explore question answering. I don't think Huifeng knows anything about biomed. I might be mistaken, but definitely the machine didn't know anything about biomedicine before he just started giving it text to read. And he evaluated on question answering. There are about 2,000 questions he asked the system. They're shown on the bottom, and it basically blew the competition away. It answered 5 times as many questions, and it had the highest accuracy. It's just amazing, honestly. So, as I said, the opportunity with semantic parsing is natural language understanding, or getting close to it, right? Take some text, shove it in the machine, and it's going to start learning. And you can use that for a variety of useful applications: question answering, natural language search, spam generation, spam detection, knowledge extraction from Wikipedia, etc. My prediction: automated knowledge extraction will become widespread. Yet again, you can tweet me on this. So I think I'm basically drawing to the end of my talk. I'm just going to summarize the take-home points for you one more time. Okay? When big data gives diminishing returns, you need better algorithms. Point 2, only use better algorithms if they will qualitatively improve your product. Intelligence comes from knowledge. Knowledge comes from learning. My prediction, smart hashing will revolutionize search. My prediction, MapReduce will be used for simple algorithms. Graph parallelism will be used for sophisticated machine learning. Lastly, automated knowledge extraction will become widespread. I want to thank the following people for letting me adapt some of their slides. And are there any questions?
One of the reasons that we don't use this deep learning is they're not complex problems like the channel portion, the multi-max machines. This is it's not all complex problems. We know efficient ways to solve them, and also we know we can reach a state that's the optimal flow. For this sort of tuning algorithm, it's like this neural network like algorithm, how to deal with that non-complexity in your learning process.
Okay, so to restate the question, he was asking, well, deep learning is a non-convex problem, which means we're not guaranteed to get an optimal solution. If we were to use a simpler model, then we would be guaranteed to get an optimal solution. Well, I guess I have two responses. First of all, do you think that language is a convex problem? It's probably not, right? So even if we can get an optimal solution, if it doesn't work, then that's unsatisfying. I guess there are, if you're talking about support vector machines, it's very hard to get them to train on more than 1 million examples. I guess I'd rather have something that works effectively, even though it might be a bit of black magic, than something that doesn't work as good. Anyone else?
If semantic hashing solves some problem I have today, are there software packages or products that non-specialists can plug in now?
I don't think there are any I don't think there are any publicly available implementations. There is MATLAB code for deep learning that you could adapt.
As a follow-up to that, how smart do you think we need to be about feature extraction and creating a hash?
So I guess you learn the most about models when they break, or when you break them. I would do the simplest possible thing and see where it breaks and then fix that.
But it seems like the model will always need to be pretty domain specific. It seems like the model will need to be always pretty domain specific.
It doesn't need to be domain specific because if like a certain word is always being used with a certain word, then it can learn that. It learns the dependencies between words. If there's one shortcoming of it is that the way it's been posited right now, it doesn't use any syntax. So it can't necessarily understand, for example, it just doesn't understand syntactic constructions.
Like word is a feature I couldn't find in the English, so it's hard to develop a word-based hash.
Oh, okay. So there are two answers. If you want to use words to search for images, well, first of all, the way it's been posited right now is you just use an image to search for related images. But second of all, the cool thing about deep learning, as I said, you can use different types of input. So what I could learn is, if I have a web page and an image, then I could say, I want them both to have the same code. Okay? So in that case, it learns the code that simultaneously encodes the text and the image. It means the same thing. So it's going for a modality in specific code. And that's another thing that's really cool about this approach. Someone else?
Go ahead.
I just had a question about deep learning.
Yeah.
So you're talking about make the graph deeper instead of wider, which seems great, but if you're talking about you have to make the graph exponentially wider. When you add more depth, you're going to get an exponential growth in edges. Are you going to get a huge growth in edges, so are you going to have to fit
You're going to get a polynomial growth in connections. It's only polynomial, but nonetheless, it can actually encode an exponential number of variations, which is where its power comes from.
The example you use for deep learning, the lower levels appear to be not so much learned technology or learned application, but more mechanical. For example, the parsing of pixels into edges and so on. Is that characteristic of the technique or characteristic of the examples you use?
It really just is a mathematical thing where it tries to just do the compression as best as possible at every layer. I think what's honestly really interesting about it is that when you look at the first level of these features that are extracted, they look like Bohr filters, the filters that you have in your eye. And this is coincidental, but also I think telling that the machine is automatically building the same representation that occurs in the cortex. Anyone else? Last question.
How do you put that context into consideration?
How do you put context into consideration? You mean like world knowledge?
So context as in, when I say the same sentence, they mean differently in the context.
Okay. So the simple answer is that whatever you plug into a standard machine learning approach is what you want to plug into deep learning. So you can get more sophisticated with the input features. If you want to talk to me about it like offline, I can do it. But essentially, whatever you plug into your shallow learning algorithm, plug it into deep learning. That's the argument. One more?
I had a question about your MetaOptimize power set example. Are you assuming that you have sets of examples that are machines being told these are related?
So I assume that if we have one article that says Microsoft buys power set, and then we have another article that says Microsoft acquires power set, that then it will jump to the conclusion that acquires and buys means the same thing, right? Now, if it's a case that acquires, or if it were like Microsoft loves power set, right? It wouldn't necessarily jump to that conclusion because it would say, oh, okay, but then the word loves is used in many different ways that don't correspond to buys. So it only will group words if it sees that they're being used in very similar ways. Yep.
So with this, if there are n different entities, then essentially there are like exponential number of permutations, right? So how does it eventually figure out? Obviously there needs to be like some kind of thresholding or where we say that these entities when after together mean the same thing. How does that work out with that?
So I forget, you're right that if we want to try everything, it would be exponential. I forget the exact complexity. It might be quadratic, but essentially what Kuhn does is he makes everything as greedy as possible to make it more efficient. So he basically says, okay, well, what are just the two things I can combine right now that I'm most confident about? So he proceeds in a greedy way to make it faster. That it?
Can you comment on the relationship between this article and the Boltzmann machines?
Sure. So Boltzmann machines, well, the original deep learning approach was based by stacking restricted Boltzmann machines. But then Joseph Turian realized that we don't necessarily need the assumptions of a Boltzmann machine, and we could deal with standard neural networks. So.
Are you familiar with Avios algorithm, automatic distillation instruction?
Who's that?
It's called Avios, automatic distillation instruction on the graph.
Yeah.
Seems similar to
I'll look it up. Anyone? Okay, thank you very much. Okay, Deep learning, there are implementations available. Semantic caching. One more thing. Implementations for everything except for semantic hashing are available. Okay. So which one specifically? So there are a variety of implementations of deep learning. I use one called Piano. It's written in Python, but then it just runs automatically to CPU, which is so very fast. Semantic hashing, you basically have to just adapt to deep learning. For the graph parallelism, you can get on the graph website to see or you basically want that one. Besides that, you want the unsupervised semantic parsing. The one with the ontology induction, I don't think it's been released yet, but the work in 2009, where I didn't show the ontology induction on the top, he released a job for that. So that's actually pretty cool.